All right. Hi, guys. Welcome to class for today. So, as we discussed on Wednesday, I will be at a research conference up in Boston. And so I will not be able to be with you guys in person Monday, the 27th, I think. So, um, that being said, that's why I'm coming to you guys on a recording. Hopefully, this lesson should not be very long. We're just going to start Module 10, which is super basic. Lots of definitions to learn before we get into the actual content. So, we're just going to take it pretty easy today. Hopefully, this should be no more than 30 minutes, maybe 45. And there will also be no math associated with this lesson. There will just be definitions. Um, the only thing that you guys have to do are like the video I've had you guys watch before. You will have to answer two questions that I ask randomly throughout the lesson. One will be partway through and one will be at the end, and that will count for your attendance for class. So watch this video in place of class on Monday, and then I'll get those answers from you on Wednesday when we are back in person. So, chapter 10. We just wrapped up acidity, which I love talking about acidity. I don't know about you guys. You might not have liked it at all, but acidity is super useful, like we talked about with the miracle fruit or with titration with those cabbage leaves, which is so fun. All of the colors that we get to use for acidity. But we talked a lot about something called a solution, but we never really gave a definition, what it means, what we use it for. So that's what chapter 10 is about. We're going to be talking a lot about solutions. The chemistry of solutions is the chapter title, and we're going to go through and list all of the definitions. So, what is a solution? Great question, guys. Um, a solution is pretty much just any sort of two things mixed together. So, I'm sitting here, cup of tea, and my tea is technically a solution because it's not just water. Normally, when we talk about solutions, they do have to be in liquid form. So, um, like if I make a lemonade mix, that's a solution. But if I make like cookie dough, we're normally not going to talk about cookie dough being a solution. We're going to talk only about liquids being solutions. So, what makes up a solution? Two things, the solute and the solvent. So, solute is what we put in, what gets dissolved, and the solvent is the thing that's doing the dissolving. So, my tea, the solute would be the actual like tea bag and the flavor, and the solvent would be water. If you're making lemonade, the solvent, again, would be water, but the solute would be lemon juice, sugar. Um, maybe it's just one of those little packet things and it's like the little powder that you just dump in and mix and stir, and that would be your solute, which is super easy. Again, with solutions, the solvents, we are normally going to talk about those being liquids. So water gets used as a solvent a lot. It's actually called the universal solvent because it can dissolve a lot of things. And then for our solutes, we can use solids, gases, liquids, whatever we want as our solute. So an example of each one of those, solute, let's say salt. We're going to make pasta. We put some salt into the pot of water. The salt, which is a solid initially, turns into the aqueous phase in our in our solution. And eventually it becomes homogeneous. You guys remember that word when we were talking about mixtures. So all of our solutions are going to be homogeneous, meaning they are all evenly mixed through and the composition is uniform throughout. If we want to think about like a gas solvent or solute, sorry, think of a soda. So we've got our liquid or like a sparkling water, we've got water, but then we actually bubble some carbon dioxide into the water. We mix in that gas with the water, it gets dissolved, and it's actually a gas solute in a liquid solvent, creating our solution, which is super fun. If you want to think about something liquid, um, this one, it could be a lot of things. Let's just say I am trying to clean some stuff in my dorm and I need to use some vinegar to do it, but I don't want to use super strong vinegar, so I put a big thing of water and I add a little splash of vinegar, a liquid into a liquid. But you're probably like, okay, how does she know what the solute is and what the solvent is? Normally, how you go about figuring out what is what is present in a higher amount. So obviously, for our salt water example, there's going to be more water than there is salt. And so there's more water. Water is then the solvent, and then salt would be the solute. If I add only a little bit of carbon dioxide into my water, because, we still want it to be a drink, we just want it to be slightly fizzy, then water, higher amount, that's our solvent, and then carbon dioxide is our solute. We'll get more into like how things work, how do we know like how things are being dissolved, because I've also used that word a lot when we talk about ionic compounds, but we don't get to explain it very often. And so we're going to talk about that in this lecture. So, first, let's talk about our ionic compounds. You guys know, classic example, um, NaCl. So, since I don't have my whiteboard, sodium chloride. They are bonded together ionically because they're attracted by the opposite charges. So we have sodium, positive charge here, chloride, negative charge. The electron has been completely transferred over here. And so we have a full positive and full negative charge, and that gets attracted together. But then, normally, we don't just talk about one teeny little molecule, we talk about a bunch. And so what ends up happening is that the molecules alternate. So we'd have like sodium, chloride, sodium, chloride, sodium, chloride, and we would make like this big block of ions put together. If you've ever looked at just like a grain of salt, you'll know it looks like a square. And that's because we're going to call that our ionic crystal. And so it's that alternating structure of the ions, and it's being held together by that positive and that negative charge. And so that attraction is the only thing that's holding it together. Remember, our electrons have completely moved over, but we don't have like in that covalent bond, you guys remember that the electrons are shared. And so the fact that the electrons are being shared kind of holds that molecule together. But ionic is not being shared. It's completely transferred over. And so now it's just that plus and minus, kind of that magnet charge that attracts the two together. But then, let's say we put that sodium chloride into water. What happens? You guys know it dissolves. What does dissolving mean? Okay, guys, great questions. Uh, Dissolving is pretty much just separating that ionic structure. So I'm going to post a picture of this into the video of how water actually dissolves these ions. So, hold on. remember that water is actually polar. So if we have our two hydrogens and our oxygens up here, remember that electron density is getting pulled up. And so we've got a negative charge on the top and a positive charge on the bottom. And so this means that water is also attracted to that sodium chloride. So the negative parts of water, so the oxygens, end up being attracted to the sodiums, but then the positive hydrogens end up getting attracted to the chlorides. And so all of these little water molecules end up pulling off the ion for sodium or chloride and surrounding it. And this is what is called solvating. Big fancy chemistry word. To solvate is to surround a molecule and help it dissolve. So the negative parts of water, the oxygen end, ends up making like a little circle around our sodium ion. And then the hydrogens, they make their own circle around the chlorides. And it ends up being fully surrounded by the ions end up being fully surrounded by the different water molecules. And the ions get pulled apart. They're no longer right next to each other in that big solid square structure. They're just free floating in the water. And now we have a bunch of positive charges just throughout the water. Okay, so that's how ionic compounds dissolve in water. But you guys also know that there are covalent compounds. So covalent compounds, those are ones where electrons are shared. So sometimes the electrons get shared evenly. You guys know this. For nonpolar compounds, you guys remember talking about polarity and how electrons get shared. So if we're looking at O2, an oxygen molecule, then we're going to see that the electrons are going to get shared equally between those two atoms because they both want the electrons equally. And so we've got those extra electrons that are spinning around those atoms that are getting shared to fill the octet rule. So they're all still stable and they're all still connected, but we're not going to be able to pull those apart because the electrons are being shared. It's kind of opposite of the ionic compounds that we were looking at. Those can get pulled apart. Covalent ones cannot. So, can covalent compounds dissolve in water then? How does that work? The answer is actually yes. So those can also be solvated. It just looks a little bit differently. So I'll put another picture up in this video to show you what it actually looks like. And this is going to be with a molecule of pH 3. So this is phosphorus trihydride. And it's very polar. So the phosphorus is pulling the electron density, and so that means it's negative, and then the hydrogens are positive again. So the water, again, polar, gets attracted to the negative end of the phosphorus, while the the negative end of oxygen gets attracted to phosphorus trihydride's hydrogens, while the hydrogens on water, because they're positive, get attracted to the negative phosphorus. So remember, opposite charges, they attract, and so they're going to be solvated. It just looks a little bit differently, and you can see that picture right here. All right, so when we're looking at phosphorus trihydride, we're going to see that, yes, even though it's not ionic, and even though the ions don't separate, we can still actually dissolve this in water. So what's our rule? How do we know, is something going to dissolve? Is something not going to dissolve? And we're going to see that this is literally a phrase that gets taught in chemistry classes for college level and above. Like dissolves like. You're like, huh? What does she mean by like? Basically, if two things have a similar polarity, they're going to dissolve each other. So water is polar. That means water can dissolve other polar compounds, but if the compound is nonpolar, it probably won't dissolve it. So water is probably not going to do a very good job at dissolving olive oil. You know how those two layers separate out? Olive oil is very nonpolar, and so it doesn't want to go into the water. It doesn't want to dissolve. And so we're going to call that insoluble. Insoluble means it doesn't want to dissolve. So um, another example of an insoluble compound would be sand. The sand on the beach is not just dissolving in the water. Sometimes it'll get mixed up by the water if the water's moving, but really it doesn't dissolve. We know that it will stay in the solid phase instead of becoming aqueous. Um, there are some other insoluble compounds. Normally, um, you can have an insoluble ionic compound, which I don't want to talk about it too much just because it can be super complicated as to knowing which ones will dissolve and which ones won't. But a lot of times it's like the heavy metals, not the rock band. Sorry, guys. We're not talking about rock music. Um, Heavy metals like lead or just look at like the bottom of the periodic table. A lot of times if you have an ionic compound with a super heavy metal, it will not end up being soluble in water. I do not expect you guys to know all the rules as to when it's soluble, when it's not, but it is at least a good gauge to know that, okay, if something is ionic or polar, if the solvent is also polar, like water, it's most likely going to dissolve. But if you know that the solute, like olive oil, is nonpolar and the solvent, water, is polar, they're probably not going to dissolve very well. So that's what I mean by like dissolves like. If the two compounds, the solute and the solvent, have similar charges, they will get dissolved by each other. But if one is polar and one is nonpolar, then they're probably not going to dissolve, which is weird. You're like, why does that work? It all just has to do with that attraction of like positive and negative to positive and negative. Um, and so it's completely dependent on what polarity your solvent is. Um, Next, we're going to talk about the three different types of solutes and really how they dissolve. So solids, that's what we all just talked about pretty much, is that solid crystal structure for specifically um, NaCl, salt. Um, that tends to separate super easily and it goes from the solid to the aqueous phase. So it gets dissolved and it's thoroughly mixed within that water. Liquids also act on a similar way. So we can take a liquid solute like lemon juice and I'm going to put a squirt of it into my tea or something. It dissolves super easily because it's also a liquid. And so if we just like shake it a little bit, if we just mix it, all of the particles get distributed super easily. But then you're like, okay, you said that gases can be dissolved, but normally we don't see that happen super often. Like, I have my cup of tea sitting here and it's exposed to the air, but I'm not seeing any gas get dissolved in it. So, why is that not happening? If you remember, gas particles are super duper spread out, um, which makes them hard to dissolve. So if I have one carbon dioxide molecule over here, and one over here, and one here, and one here, they're not as close as if they're all packed super nice into a solid little structure. So it's much harder to dissolve it when everything is super spread out. So do any of you guys have one of those like little soda stream bottles at home? Like you can make your own sodas and you like add flavoring and you can carbonate your water by yourself. So my mom has it. She loves it. I'm not a huge fan, but the chemistry works because on the back of that machine, you see like a little compressed air cylinder, and we get them delivered to our house randomly, and they're super heavy because it's this metal canister that just contains compressed carbon dioxide. So we have a polar gas and compressed, we're just going to take all of the molecules and shove it into this tiny little container. So it shoves all the molecules closer, and then we'll stick it into the back of the soda stream. And once you stick the bottle into the water, some of the carbon dioxide can leak out into your water and get mixed up because now all the molecules are much closer together and it can dissolve. And actually, like the attraction between the polar part of carbon dioxide and the polar water actually works now instead of just kind of sitting out in the air and there's not enough carbon dioxide compressed to actually make its way into my drink. A little bit extra work to get it to dissolve, but you can do it. So, in your book on page 355, there's like a little table. I might put a picture of it up on the video, and it has the requirements for dissolving. So you guys should know these. Um, let's say our solvent is liquid, but our solute is solid. In order to dissolve it, the has to be attracted to, or the solid solute, tongue twister, guys. The solid solute must be attracted to the solvent. So it has to be polar or ionic compounds. That way, the solvent can pull apart the ions or to solvate the covalent compounds. If it's a liquid, it follows pretty much the same rules. We don't really have to do much effort. We just kind of have to mix a little bit, and the two will dissolve as long as we follow those same rules of the polarity matching. Last one, gases. Not only do we have to follow our polarity rules, we also have to shove our solute, our gas molecules, closer together to get it to dissolve. All right, here's a good stopping point for our first question. And my question for you guys is, what's your favorite season? I know that's really, really basic, but I've heard a lot of people complain about the cold, but I've also heard a lot of people really wanting more snow. What your favorite season is? Mine is spring, even though I get terrible allergies, but I just love spring. So, if you guys could write that answer down on a sheet of paper and then bring it into class on Wednesday. That'll count for part of your attendance. Good? Okay, awesome. Give me a sec. All right, I've talked about um, our polarity rules a lot. So it has to be polar and ionic, or polar or ionic, in order to dissolve in a polar solvent. But some things are different. So you guys know that sugar is super soluble in water. Have any of you guys ever made like, like those rock, like sugar candies where, or like the rock crystals? I'm blanking on the name, but if you stick some sugar into water and then you put a stick in so that it can like actually attach to it, you can make like these hard candies like rock crystals. And it's really just sugar plus some food coloring. But sugar, it takes a lot to do it. It's not like you're going to put one spoonful into a big pot of water and you're going to see those crystals start to form. Like it takes a lot of sugar in order to do it. Same thing with salt. You can dump a lot of salt into water and it will still keep dissolving. But if you put baking soda into water, normally it doesn't dissolve very well. Um, and this is what we call solubility. So solubility is the maximum amount of solute that can dissolve in a certain solvent. So the max amount of solute in one certain solvent is called solubility. So baking soda, its solubility is low. It still dissolves. Some of it still dissolves, but sugar has a much higher solubility because a lot more of the solute can get dissolved in the solvent. So we're going to talk about solubility a little bit and what it means and how we can kind of change it. So in your book, um, it talks about like the definition of solubility and it gives an example. So it actually says at room temperature, NaCl, salt, can dissolve 37 grams in 100 grams of solvent. So if we have 100 grams of water, that's 100 milliliters. If I have a small beaker, normally it's about like that much water, we can put 37 grams. That's like putting 37 paper clips worth of salt into that water and it'll fully dissolve. We're not going to see any solid still stuck on the bottom. All of that salt will get mixed in. But if we do baking soda, its solubility is actually only 12 grams per 100 mils. So big difference there. Super important. We're going to talk about why, but you heard me just now use the terms or use like the units of like however many grams per however many milliliters of solvent. So we kind of can use it in like terms of concentration like we talked about. So you guys remember molarity, super fun. Or if you want to do grams per milliliter, normally that's how we would talk about solubility. So I would say 37 grams of sodium chloride can dissolve in 100 milliliters of our solvent, which is water. So a lot of times we'll talk about solubility in grams per milliliter. And always remember that solubility is dependent based on that polarity. So it depends on both the solute and the solvent for how much is going to be soluble. Oh my gosh, a lot of S words. But it's okay. If you guys get your definitions down, a lot of times it makes it easier as to figure out, okay, what are we actually talking about? I'm gonna keep adding a few more terms for you guys. One of them is called a saturated solution. So that is the maximum amount of solvent that has been, or maximum amount of solute has been dissolved in the solvent. So um, if we have 100 mils of water and we add 37 grams of salt, that is completely saturated. We can't add any more salt. So if I add another 2 grams of salt, that salt is not going to be able to dissolve. It'll just sit on the bottom and we'll have salt at the bottom and then we'll have really, really salty water just kind of sitting on top of it. But that water portion, because we know we have the maximum amount of solute dissolved, we're going to call it saturated. If we don't add that full amount, so if we only add, let's say we added 10 grams of salt into our water, we're going to call it unsaturated because we can still add more. So there's more room for salt to be dissolved, and so we're going to call it unsaturated. There is also a fun third way. So you're like, okay, not enough. We're at our max capacity, unsaturated, saturated. There's a fun little third mystery category. It's also called supersaturated. So turns out in some cases, you can actually dissolve more than the max limit. Um, So I've already talked about like that rock sugar candy. That's what we're going to call a super saturated solution. So we put a bunch of sugar in our water, we dissolve it, we heat it up. When we add heat, more stuff can dissolve. And so we're able to get more solute dissolved than what's normally possible. And so we're going to call that super saturated. It is pretty rare. A lot of times it doesn't happen naturally. A lot of times humans do it just for fun. They'll create super saturated solutions for, um, I guess, to make candy is one of them. But um, yeah, it's not really just naturally occurring. Um, but I talked about, so we heat things up and we can add more. There are a few things that change the solubility or how much solute can get dissolved. And it depends on if your solute is a solid, liquid, or a gas. So we're going to first talk about temperature. Solids and liquids. If you make the temperature increase, so we're going to heat up our water, you can normally get more solid and more liquid um, to dissolve or in the solvent. Sorry, especially solids. Solids are probably the most affected by temperature. So as we heat things up, it is a lot easier to dissolve it. So um, yeah, that's why we'll like heat up tea. So I know I've used tea as an example a lot, but normally I don't make a cup of tea by putting a room temperature cup of water and then just putting the tea bag in because things don't dissolve. But if I put boiling water with my tea bag, all of a sudden all of the flavors and all of like the spices actually will get put into the water and will dissolve. However, so that's solids and liquids. We're going to say gases are the opposite. So as we get hotter, gases actually don't dissolve as well. And you guys actually know this already. You just don't realize that you do. And guess why? You know, because of soda. We keep soda in the fridge. Normally, it's more enjoyable to drink a cold soda because it's more carbonated. But if you leave that soda out on the counter, you know what happens? It gets flat. Flat soda is when all of the carbonation leaves. So there's no more gas dissolved in the water. And so it turns flat. It turns back into pretty much just a basic liquid. There's no gas dissolved in it. And what was the difference? In in the fridge, we were keeping that carbon dioxide cold, and so it wanted to stay dissolved in the water. But once we set it out on the counter, room temperature, opened up the lid, it got flat really fast because um, the gas was not as soluble in water because the temperature was increased. So if you want to keep your carbonation, keep your drink cold because things will stay dissolved a lot better um, than I guess if you heat it up. But there's also a second thing that can increase or that can affect the solubility of gases. So I just said if you leave a soda out on the counter, it's going to get flat. But if you go to the grocery store, normally soda isn't kept in the fridge. You're just going to go to Walmart and you're going to pick up an entire case of unrefrigerated soda. And you get it, and it's not flat. What actually helps the gases stay soluble is the pressure of the container. So we've got our bottle of soda and the lid is screwed on super tight. No gases can get out. And so then the gases stay in the solution. There's a lot of pressure in that bottle because you know, if you shake that bottle and then open the cap, it'll spray. So you've probably had this happen by accident. You open up a Coke and it just starts spraying everywhere because it accidentally got shook and the pressure was too much. And so it just explodes. But in normal scenarios, the pressure of that bottle is enough to keep the carbonation trapped inside the can. But once we open up that can, the pressure gets released. So we pop that top off, and now the pressure can escape into the atmosphere. It's at a normal atmospheric pressure, and that's when we start to get worried about sodas getting flat, is once we've opened that bottle initially and we leave it out in a warm area. Now we don't have pressure and we don't have temperature, or the right temperature, in order to keep things carbonated. So that's our rule for pressure. So if we keep things under pressure, it will increase the gas solubility. But normally, for solids and liquids, we don't talk about pressure super much having an effect. And you're like, why? That's because, remember, we have to keep our gas molecules close together in order to dissolve it. So pressure is going to push all of the molecules super close, and now they'll be able to dissolve. But if we don't have an external push of pressure, nothing's going to happen. And so we won't see any gases being soluble. So that is all I have for you guys today. That wraps up all the material I wanted to cover. I will also be sending out an additional video by Chad's Prep. You guys, I know you might be getting tired of him, but I love his videos. They're super helpful. Probably a little bit shorter than what I just gave you, but a good review and a good way to get the definitions under your feet in order to keep things straight, because we're gonna use the terms solute and solvent a lot through the rest of the chapter, and you're gonna need to know them. So that is the last bit of the lecture for today. Your second question that you're gonna need to give an answer for on Wednesday is, one, are you reading a book right now? And if you are, what book is it? So I am currently reading, called Recapturing the Wonder. It's for class. It's for one of my classes. So that's the book I'm reading. If you're not reading a book, just be honest. Tell me you don't like reading, which is great. Some people don't, and that's cool. So on Wednesday, you should have watched this video and given me the responses to the two questions. So what's your favorite season and what book are you reading right now? And I'll mark you fully present for class. There's no worksheets. There's obviously no practice sheets because there's no math that I just gave you, and no on your own due. So I will see you guys in class on Wednesday. And I hope you guys get a little bit of extra rest today without having to come into class. So have a great day, guys, and I will see you on Wednesday.